chapter 15 of our marine electricity hammer. The chapter 15 is related with inverters. If you remember, there are three types of sources of AC power in a typical boat. One source of power is the shore power. That's the power coming from the pedestal, the power coming from the dock. The other source of power is the generator. Single phase, double phase, three phase, diesel or gasoline. The generator produces exactly the same type of power coming from the dock. AC power, AC signal. Both signals are perfect signals, clean signals. The other source of power is the inverter. The inverter, this one or this one, is an equipment that converts DC power into AC power. The output AC power enters into the switch selector. In the switch selector, you can select inverter or generator or shore power, depending if the power is coming from the shore, or if the power is coming from the generator, or if the power is coming from the inverter. This is the switch selector. After the switch selector, the output of the switch selector enters into the main breaker. This is the main breaker of the boat. And after the main breaker, you have the single breakers or specific breakers. Breaker for battery chargers, for lights, for appliance, different breakers. Single breakers, and this is the main breaker. In this chapter, in this episode, we are going to be concentrated in the inverter. How the inverter converts the DC current, positive and negative DC coming from the battery, into AC power, hot, neutral and ground for single phase, or hot, neutral and ground for double phase or three phase. This is an equipment, this is an expensive equipment with an special characteristics. We are going to study in details how the AC power is produced on the inverter and why, in my opinion, the inverter is not efficient in a typical boat. I recommend the inverter for backup, but in general, I recommend basically the generator. The generator is, in my opinion, the most important source of AC power. Of course, the power from the pedestal is the number one, number two, the generator, and number three, the inverter. How the AC signal is produced on the inverter? Let me explain to you something about that situation. Suppose that this is the DC signal. That's the positive side of the DC signal, and this is the negative. Voltage and time. If you interrupt the positive signal in sections, if you cut it, the signal with the transistors and capacitors, the positive and the negative with transistors and capacitors, you cut it, and after that you pass that current, interrupted current, through a coil, and the coil is the primary coil of one step-up transformer. This is a step-up transformer. If you remember, in our previous chapter dedicated to transformers, I explained to you there are three types of transformers: isolator transformers, step-up transformers, or step-down transformers. The step-up transformers, in the output, the voltage is higher. The step-down transformer, in the output, the voltage is lower. Suppose that this interrupted signal enters in the primary coil of this step-up transformer. This step-up transformer increments the output voltage 10 times. Okay, what is the meaning of that? That in the secondary of this step-up transformer, this transformer produces a signal 10 times bigger than the input signal. For example, if the input signal is 12 volts, the output signal will be 120. What is the inconvenience? That signal is basically the connection of those segments. It's basically a square signal. The electronics engineers, they modify those corners. They rounded those corners with the resistors and capacitors. And at the end of the day, they produce a simulated signal. That simulated signal is not a perfect sinus signal. It's pretty close. What is the inconvenience with that signal? What is the most important inconvenience? The inconvenience with that signal is, okay, at the end, the shape of the signal is pretty close to the sinus signal. But that signal doesn't have frequency, no frequency. What is the meaning of that? With that signal, it's difficult to produce rotation. Remember, frequency is produced for RPMs. When the rotor with the magnet is spinning in front of the stator, produce the AC signal, the sinus signal. In this particular case, we don't have electromagnets in rotation. We produce that signals in a circuit board. We interrupt the DC signal. We pass the signal for the step-up transformer, and we simulate that square signal. We round it, but that signal doesn't have frequency. This is the inconvenience of the signal produced on the inverter. How are the signals produced on the output of the inverter? Those are the most typical signals produced in the output of the inverters. Square signals, or triangle signals, or a signal like this, small segments. This is the best. In our class of electronics, we are going to use the oscilloscope to check the output signal of the inverters to verify, and we are going to verify that this is the typical output signal produced for inverters. Depending of the quality of the inverter is the output signal. There are inverters with high quality, but those inverters are expensive inverters. And there are inverters, cheaper inverters. Those inverters produce triangle signals or square signals. Depending on the quality of the inverter, the output signal is better. For that reason, you found that inverters that they say in the label pure signal or perfect signal. It's not pure, it's not perfect. It's pretty close to the sinus signal, but the output signal is not perfect. Okay, what is the meaning of that? The meaning of that is, with the power produced for the inverter, it's not possible to supply power for the entire boat. In other terms, I don't recommend a supply power for air conditioning equipment coming from the inverter. The power coming from the inverter is good for a small appliance, for small blowers, lights, computers, laptops, electronic equipment, but it's not good for heavy pumps, heavy motors, heavy compressors, because those equipments require perfect signals, because those equipments need perfect rotation on the pumps, perfect rotation on the stators. For that reason, I am going to explain later what is the procedure to install the inverter, what type of breakers on the panel should be recommended for the inverter, and what type of breakers are not recommended for the inverter. I am going to explain the procedures to calculate the capacity of the inverters in kilowatts, and I am going to explain the procedure to install the inverter on the boat. Remember, the inverter is one of the three sources of AC power. One source of AC power is the shore power, the second one is the generator, and the third one is the inverter. The inverter have a couple of inconveniences. One inconvenience is that the output signal is not a perfect sinus signal, it's like a little square, and additionally, the output signal from the inverter doesn't have frequency. For that reason, the power produced for the generator is used only in emergency, and is used for some equipment, not for all the breakers in the AC panel. Why? Because if you use the power produced from the inverter for all the breakers, you need a lot of batteries to supply power for those equipments. I am going to explain right now the procedure to calculate the capacity of the generators in kilowatts. I have one example And with that example, we are going to follow the procedure to calculate the batteries that you need in order to supply that amount of power. In general, if you want to install a new inverter in a boat, I recommend take a meeting with the owner of the boat in order to be 100% sure how many equipments and for how long time those equipment should be connected in the future. After that meeting, you make a list of the equipments that we are going to supply power with the inverter. For example, in this situation, the customer said that we are going to supply power for those equipments. One air conditioned equipment, one refrigerator, one freshwater pump, one water maker, 5 blowers, and 2 appliances. Those equipments in total, they need 80 amps. 80 amps. 20 for the air condition, 10 for the refrigerator, 10 for the... In total, 80 amps. Okay, if the boat is double phase, 240 volts, and the amps are 80 amps, how much power I need? I need 240 volts times 80 amps. I need 19,200 watts. I need 20 kilowatts. Oh, I need an inverter of 20 kilowatts. An inverter of 20 kilowatts is an expensive inverter. Okay, but no problem. The customer approved by an inverter of 20 kilowatts. And now I need to know how many batteries I need to supply 20 kilowatts for 1 hour, 2 hours, 3 hours. This is the procedure. The inverter, normally, this is the typical connection of the inverter. The inverter at the input receives power from the group of batteries. The group of batteries, they have a main switch. This is the switch. It's a typical main breaker or main switch like this. In order to connect and disconnect the power, the input power DC to the inverter. The input power DC enter into the inverter, and the inverter convert the power into AC power. That source of AC power goes into the switch selector in the position inverter. There are other positions for short power and other positions for generator. Okay, in this particular case, the DC power is converted into AC and enter in the position inverter. All right, I need, according with our example, 20,000 watts. I need 20 kilowatts. All right, this is the power that I need in the AC side, in this side. The power should be the same. The power produced in AC is coming from the power entering in the DC side. Okay, if I need 20 kilowatts over there, it's because I have 20 kilowatts. What is the formula for power? The formula for power is voltage times intensity. Remember, if I need 2 phases in the output, 240 volts, normally the configuration in the input DC should be 24 volts. Because remember, in the previous episode, we have a step-up transformer. If I have 12 volts in the batteries, I am going to produce 120 volts. If I have 24 in the configuration on the batteries, I am going to produce 240 volts. Okay, I am going to connect those batteries in series in order to produce 24 volts. 24 volts times the intensity that I need DC should be equal to 20 kilowatts. In other words, the intensity that I need in DC should be equal to 20,000 divided by 24. And this is the amount of amps that I need in my battery bank. All right, for safety factor, the recommendation is in the input, put exactly the same like the output plus 20%. For safety factor, because some power is dissipated in heat, some power is dissipated in the circuit board of the computer of the inverter. For that reason, it's important add 20%. How can I add 20% easily? Okay, the recommendation is, okay, we are going to divide it, no for 24, we are going to divide it for 20, and this is the safety factor. Okay, it's 20,000 divided by 20, 1000 amps. This is the amount of amps that I need at the input of the inverter in order to produce 20 kilowatts in the output. 1000 amps in order to produce power for 1 hour. Oh, I need those equipments working constantly for 3 hours. Oh, you need 3000 amps. Okay, how can I get those amps? That situation depends on the type of batteries that you decide connect on your boat. I recommend, that's my recommendation, use golf cart batteries, because the golf cart batteries have a big capacity of storage, big capacity in amps. The golf carts batteries are available in 6 volts, 8 volts, and 12 volts. If the battery is less voltage, 8 volts or 6 volts, they have more capacity in amps. You can enter online and you can select golf cart batteries, and you can organize the batteries in series or parallel in order to get those 1000 amps or 2000 or 3000, depending how many hours you want to supply the power at the AC panel. Okay, we are going to refresh the procedure. The procedure is simple. The first step is select how many equipments in the AC panels will be powered from the inverter. Okay, 1 air conditioning equipment, 2 blowers, 1 refrigerator, 2 lights. You added all of them, you added the amps, and those amps you multiply times the voltage of the boat. In this particular case, 240 times the amps. This is the power AC that I need. Okay, that power AC should be equal to the power DC coming in, but the power DC should be a little increased, 20% normally, in order to produce the output power. Okay, the output power, 20,000 kilowatts, should be equal to the input power. The input power is 24 volts, because I am going to organize my batteries in 24. I wanted 240 in the output, times the intensity. And this is the intensity in amps that I wanted. Okay, the intensity is 20,000 divided by 24. Okay, I don't want divided by 24. I'm going to divide it for a small number in order to get more amps. Okay, I'm going to divide it for 20 for safety factor. And this is the amount of amps that I need in my group of batteries to supply power for 1 hour. This is the amount of amps in order to supply power for 1 hour. Remember the rule, never discharge a battery more than 50%. That's the rule. You need to be careful with that. All right, this is the configuration, the installation of the inverter. That's the input. Remember the breaker at the input, and this is the output. Now I want to explain something about yours. Normally the inverters, the marine inverters, they have on the label, the inverter, the label says inverter / charger. And normally if you check the AC panel of any boat, if you check the AC panel, this is the AC panel. The power from the AC panel is coming from the switch selector. The switch selector receives power from inverter, or from shore power, or from generator. Okay, normally in a typical boat, on the AC panel, you found one breaker with the label inverter / charger. Some people say, this is the breaker in order to activate the inverter. No. The inverter is activated, remember, from the switch selector that supplies the DC power. This is the breaker or switch selector used to activate the inverter. The switch selector is located here in order to interrupt the positive at the input of the inverter. That's the input. That's in some cases you install, instead of the switch selector, you install one breaker. That's the breaker to activate the input of the inverter. In the output of the inverter, the majority of the inverters, they have 2 divisions. They have hot line, neutral and ground for output, and they have hot line, neutral and ground for input. What is the meaning of that? They have output AC and input. Okay, the output AC is the cable that goes directly into the switch selector of the boat. And the input AC power is power coming from one breaker of the AC panel dedicated to activate the small battery charger located inside of the inverter, used to keep those batteries fully charged. That power coming from that breaker is only to activate the battery charger located in the inverter, used to keep those batteries fully charged. When the inverter is running, when the inverter is activated on, the inverter is producing power and this input is closed. No receive power because in this moment the inverter is producing power. Okay, we are going to refresh. In the output AC, we have two groups of outlets. One outlet for output power and other one to receive power in order to activate the battery charger. This is the typical configuration. This breaker, inverter / charger, located in the AC panel of the boat, is used only to keep the charger of the inverter working in order to keep the group of batteries fully charged. The other group of outlets those are the outlets to supply power to the switch selector. This is the typical way to configure an inverter and the typical way to install an inverter. What is the recommendation? This group of batteries should be independent group of batteries. Those batteries should be dedicated exclusive for the inverter. What type of batteries are recommended for an inverter? Deep cycle batteries. Deep cycle batteries are excellent. I don't recommend use cranking batteries. Why? Because the cranking batteries deliver the amount of electron faster, and you wanted to deliver the amount of electron slowly. Deep cycle batteries are excellent. And also I recommend heavy golf cart or forklift batteries. Those batteries have a big capacity to store as electron. For example, this battery is a Series HD. This battery is an excellent battery. This battery have a capacity of 800 amps per hour. It's a good capacity. Or those batteries are Series 27. Those batteries only have 100 amps per hour. In this particular example, I need 1000 amps per hour. Okay, with two batteries of this, I have 1600 amps per hour. This is a good selection. The secret is select the appropriate batteries in order to keep a good group of batteries properly installed, properly organized, in order to supply the amount of AC power required for the customer in the boat. It's important that you explain to the customer that the AC power produced for the inverter should be backup power. The main power should be the power coming from the generator. The generator is a good signal, it's a clean signal, and the idea is keep the generator supplying power constantly. For that reason, in the majority of the big boats, you have 2 or 3 generators. In a mega yacht, you have normally 3 generators. Each generator is running 8 hours. After 8 hours, the first generator stops, and the second one starts and supply power for other 8 hours. At the end, the generator number 3 starts, and the other ones are stopped. And once again, the cycle continues with the number 1, number 2, and number 3. Each 8 hours, one generator is running, and the boat supply power for 24 hours. My recommendation is never run a generator more than 8 hours, more than 10 hours maximum, because the generator is a diesel engine or gasoline engine. Run the engine more than 8 hours is not good for the engine. Doesn't matter if the oil is synthetic and the refrigeration is good. You need to stop the generator, relax the generator, and run another generator for other amount of 8 hours. A couple of additional things related with the ABYC study guide specific for the chapter 6 inverters. In the ABYC study guide chapter 6, there are important recommendations that I want that you read carefully. For example, one of the recommendations is in relation to the capacity of the inverter according with the capacity of the battery bank. the capacity of the battery bank for any type of marine inverter should be no less than 800 cca. 800 cca is the minimum according with ABYC. Other important recommendation is install the inverter separate as close as possible to the battery bank, but not over the battery bank. It's logic because if you install the inverter over the battery bank, the gases, the fumes from the batteries affect the circuit boards on the inverter. Other important recommendation is in relation to the marine inverters. Always install marine inverters. Why? Because the marine inverters, they have the neutral and the ground connected together internally at the source of the power, and you don't have any problem after that in the boat. If you use industrial inverters or residential inverters, those inverters, they don't have the neutral and the ground connected internally, and probably you need connect externally, and that's confused. Use always marine inverters. Other inconvenience is that the inverters produce too much electromagnetic interference, a lot. For that reason, be careful when you install the inverters and where you install the inverters inside of the boat. Try to keep the inverter separated from the compass, from any electronic equipment, radar, transducers, affect the transducers dramatically. Try to install those elements in a separate, the inverter specific, in a separate compartment away from any electronic device, because the electromagnetic interference is high. How can I know if in this point I don't have electromagnetic interference? Try to use the Gauss meter. You have the Gauss meter right now in this corner, and this is the element used to check how strong is the electromagnetic interference in this area. This equipment is the ABYC recommended equipment to verify how strong is the electromagnetic interference in this area. The Gauss meter. We are going to use the Gauss meter. Other important recommendation that I found in the ABYC study guide is in relation to the AIC rating. The AIC rating. This is basically it. The AIC rating is the amount of amps that a fuse or breaker can support before the contacts of the breaker be welded together. The amount of amps that a fuse or breaker can support when the contacts are closed before those contacts be welded together. ABYC have an example. ABYC say, for example, a fuse class T is rated with a 20,000 amps AIC. However, the nominal rating for that breaker, for that fuse, is in between 200 and 300 amps. In general terms, what is the meaning of that? In general terms, any breaker, for example, I have a breaker like the breaker that we have right now in the screen, for 200 amps. That's the number on the handle of the breaker, 200 amps. That breaker, internally, the AIC rating is for 2000 amps. What is the meaning of that? If that breaker have the contacts closed, that breaker can support until 20,000 amps before internally the contacts be welded. This is the meaning of AIC. And ABYC recommend install a fuse class T in between the battery bank and the main breaker at the input on the DC side, on the DC wire. In between the battery bank and the switch selector or main breaker, you install the fuse in order to protect the inverter. Very, very, very important recommendation. Any other recommendation? No. This is basically the most important recommendations. the minimum capacity of the battery bank should be 800 cca, and the electromagnetic interference, I mentioned that. Use marine inverters always, and those are the most important recommendation of ABYC in relation with inverters.